Hi, I'm Hannah, and in this lab I analyzed the motion of a mass attached to a spring that both oscillates vertically and swings horizontally. I compared the experimental data to a computational model and tested whether energy is conserved. I found that the model closely matches the motion and that total energy remains approximately constant, confirming the energy principle. The system is modeled using Newton's second law, F equals ma. The forces acting on the mass are gravity and the spring force, which depends on how much the spring is stretched. The spring force always acts along the direction of the spring. These forces determine the motion in both the x and y directions. I modeled the system as a point mass attached to a massless spring, ignoring air resistance. The motion was calculated numerically using small time steps. These assumptions simplify the system while still capturing the key physics. I recorded the motion and analyzed it using Tracker. I calibrated the video using a known length and extracted position data in both the x and y directions over time. The initial position and velocity were taken directly from the first data points. The initial position was negative 0.0127, negative 0.703, and then 0 in the z direction. The initial velocity was 0.05, 0.8, and 0 meters per second. The mass of the spring is 0.402 kilograms, and the equilibrium length is negative 0.7 meters. The velocity was estimated using a change in position between the first two frame agreements. The model calculates forces at each time steps and updates the velocity and position using Newton's second law. The spring force is calculated based on the current length of the spring. The forces are taken from known force equations, like negative Ks times L hat for this force of spring. The model and experimental data show similar oscillatory behavior in both directions. The agreement is strong, though small deviations appear over time due to experimental uncertainties. The kinetic, gravitational, and spring potential energies change over time, but the total energy remains approximately constant. This indicates that the energy principle is satisfied. To analyze the oscillation periods, I used the tracker data for x and y positions. The period is the time between two successive peaks in the motion. For the horizontal motion, the first negative peak occurs at index 5 and then at index 47, multiplying the difference in indices 42 by the time step delta t equals 1 over 210, or 0.00476 seconds per frame, gives an x period of approximately 0.2 seconds. For the vertical motion, the first maximum occurs at index 11 and then next at index 39. This gives a time of 28 times 0.00476 or 0.133 seconds. These results make physical sense. Vertical motion oscillates faster because the gravity adds to the spring's restoring force, whereas horizontal motion is slower because it's only influenced by the spring in that direction. Overall, comparing the periods from x and y motion highlights that the system exhibits coupled two-dimensional oscillations with different frequencies in each direction. Differences between the model and experiment may come from calibration errors, air resistance, and the assumption of an ideal spring. The time step in the simulation can also introduce small numerical errors. In conclusion, the computational model successfully predicts the motion of the system. The total energy remains nearly constant, confirming conservation of energy, and the system exhibits coupled oscillations in both x and y directions.